This conference will now be recorded.
So today's session, we are going to have a look at some topics, but like just an overview of like 3 or 4 topics together. So we are not going to go too deep, but we will understand how they work. First topic, semantic segmentation. Before that, we did what we call classification or regression. You get an image and you tell if there is a cut in it or not, like this one. But with semantic segmentation, what do? We try to find the pixels that constitute the cat. For classification, we just tell this is a cat. The whole image contains a cat, but we don't know where it is. For segmentation, we clearly tell what pixels constitute the cat, like in here. So we tell that this is the cat, this is grass, this is whatever it is, trees or something, and this is sky. So we tell each pixel what it is. It's a lot harder than just saying that this contains a cat. Because when you say this contains a cat, you may just look at the ears, the eyes, and the nose, and you can tell if it is a cat. But to tell you what pixels are, this is a more complex problem. So how do you think we can do it? We talked about it last time a little bit, but tell me, how would you like do this? How would you like tell what each pixel it is? Looking at and just the color is not enough. Yes or no? Do you agree with me?
Yes.
Yeah, looking at just the color, a white color can be the cloud or the cat itself. So the color itself is not enough.
Yeah, it's common between the two features.
Exactly.
Yeah.
So the white here in the cat or the white here are very close to each other, or the sky. So the color is not enough. We have to do something different.
Texture.
Yeah, we can, for example, look at the neighborhood. So we take the color and we look at its neighborhood. What do we have next to it? And we can maybe classify it. This is also a possibility. But it's generally, it won't produce some perfect results by just looking at the neighborhood, because still, if we take this neighborhood, it's still all white. If we make it bigger, it starts becoming easier to understand. But if we take a small neighborhood, it will be still difficult to know what pixel this is. And also, if we use the neighborhood, we will have to do the same thing for every pixel. For example, to classify this pixel, we look at all the neighborhood next to it. Then when we look at the pixel just next to it, we have to look at everything again. So there is a lot of work to classify every pixel. Don't you agree?
Yes, yeah.
Yeah. So there is a way of doing this by convolution. So here, as you can see, we have the image, and we send it through convolutions, a series of convolution. And here, so every convolution layer is going to detect some shape. And here, in the last convolution layer, each slice, this is the activation map, each one will be specialized in telling us what's this like shape it is. So this one is, for example, focusing on this part of the image. It will tell us what it is, what type of shape it is. So in normal convolution, what's the difference between these layers? What's the difference between them? What kind of shape this layer is able to detect? What kind of shapes, guys, is this layer able to detect? Simple shapes, complex shapes?
Less complex, yeah, simple.
Exactly, like horizontal line, diagonal line, etc. This kind of lines. And this one is able to detect things that are a little bit more complex.
Yeah, more complex.
And so on. This might be able to detect ears, eyes, etc. And this one is probably able to detect something even more complex. So what we are doing here, we look at this layer and we see what were we able to detect cow, sky, etc. Something that is more complex than here than in here. So this layer will tell us this is a cow, for example. This is the head of a cow. It's because a cell is focusing on something that looks like a square, because it's taking like a square-like things. So this is focusing on a region. Let's say now it is focusing on this head. It says this is a cow. And why are we taking the argmax? Because another layer is trying to detect the sky, like this one. And this layer is probably able to detect grass. So it can say if this is grass or not. So when we take the argmax, let's say we have this pixel. This pixel here is in here, and we have values here. So the higher the value, the higher the value means what? The higher the value, what does it mean when we have high values?
It means we are like more sure that it's like this shape or like something.
Exactly. It means that we are very close to this shape. Yeah. So, and it's not probabilities, but it's just like a score. It's just like a score. So the higher the value, the more closer we are. If we are detecting here, like the head of a cow, here we are detecting maybe the grass and then the sky. So if this value is high here, so let's say 10, 1, 0, it means it is the head of this cow, probably. So this is what argmax means. So we take the maximum. So this is position 0, this is position 1, this is position 2. So when we take the argmax, what we will have here, 0, 1, or 2 for this pixel?
2.
0.
Oh, sorry. Yeah.
Because it's 10. It's
the position you mean. Yeah. Sorry.
Yeah. We are taking the position. The position
10, 1, 0. Yeah, it's 10. Yeah.
So here it will be class 0. Another pixel like this one will be class 2, because here it's higher. Here it's maybe 5, 0, 0, 5, 0, 0. So it will be class 2. And then we build a matrix that contains the number of the class. So we can say class 0 equals brown, class 2 equals blue. So we just color it by any color, just to make them different. So every class will have its color. We give it by ourselves. It's up to us to choose what color to use, and we end up with something like that. It's like we have here what we detect in terms of complex shapes, and we take the maximum. The maximum will tell us what class, what pixel, and what class it is, because each value represents like the complex shape. So what did you see here? Do we have any like fully connected layer?
No.
No. As you can see, this is called an FPN, an FCN, sorry, a full convolutional neural network. This type of networks are called FCN. There is no fully connected layer, just convolution layer. And from it, we just apply the argmax, and we get our thing here. And we get our segments. So this is the cow segment. This is another one, etc. So this is what we call semantic segmentation. Sometimes the input size is very big, can be huge, the image size. You remember last time when we computed the weights and the memory requirements, we said that the memory requirements are very high at the top of the convolution layer, because we have like the images can be big, and the memory requirements to start things with the first layers can be high. So what can we do? We can have a neural network or a fully convolutional layer, the FCN, like this, But what we use here to make it smaller, what do we use? What are we using to making it smaller? The max what layer makes the network smaller?
What was it?
What layer makes it smaller? The max pooling, if you remember it. Are you with me?
Yeah. It was the max pooling, which
the max pooling
layer.
So
the dimensions, yeah.
Exactly. So when we use the max pooling, we are reducing the dimension. So we can have a smaller network, because if we keep things the original size, we will have some problems. So we do some layers, then a max pooling, some layers, 3 layers, and a max pooling. And what we do the upsampling again. We make it bigger now. So here, this layer is detecting more like complex shapes, but when we use the max pooling, we have it smaller, which is normal. Complex shapes take a bigger size. So we can, like from an intuitive point of view, it's correct, because we are trying to detect what complex shapes we have. We are losing a little bit the spatial representation, but we still have it somehow. We have some spatial representation that is not precise, but it is still there. And then what we do at the middle, we upsample again. So here we have the complex shapes, and then we are upsampling until we get the original image.
Yeah, sorry. So for downsampling, we are using max pooling to reduce the dimensions. What are we using for upsampling? Sorry, I'm lost.
That's a good question. It is coming next on the next slide. And there are ways to do the upsampling. Some ways that are the opposite of the max pooling.
Oh, okay.
To do the upsampling, yeah. And they exist, like in Keras or any other thing. It's a special layer that does this upsampling. Like something that is the reverse of the max pooling. Let's have a look at them. So we can use what we call end pooling. This is one form of the end pooling. To make this bigger, we just duplicate this 4 times. This is what we call nearest neighbor. We just duplicate it 4 times. We have what we call also the bed of nails. We keep it in a corner and fill the rest with zeros. These are 2 possibilities. There is also the max end pooling. When you look at here, we know when we apply the max pooling in this layer, from here to here, or from here to here, when we apply the max pooling from one layer to another, we know which one was kept. For example, here, when we apply the max pooling to this quarter, we know that this corner was kept. In this quarter, we know that this corner, this value was kept, like here. So we know which one it was kept. So when we do the max end pooling, because it has like every end pooling has its own counterpart, like here, this one with this one, and this one with this one. There is like a symmetry here. So we do the same thing again. So in this value, 1, 2, 3, 4, when we end pool, we put that one in its position, the same position that was used in its original counterpart. For example, here, that was what we used for the max pooling. 1, 5 was kept in here. The 1 will be put in here, and all the rest will be zeros. You can see here, we took the 6 in this from this position. So with the 2 here, to do the max end pooling, it stays in its own original position, and we put zeros in here. So Emma, can you see here? Can you?
Yes, yeah.
It's very clear, yeah. So we keep the original positions for the max end pooling, and all the rest will be zeros, because we don't know what number to use. So this is for the max end pooling. One way of doing it. There is a more clever way.
Sorry. Can you just explain again the how we do the max and pooling? Yeah, thank you.
Yes. So let's take the first half. The first half is a simple convolutional neural network.
Yes.
There is no fully connected layer. A simple convolutional neural network. So from here to here, we did the max pooling. From here to here.
Yes.
And from here to here, we also did the max pooling.
Yeah.
Yes. Here it's the regular layers.
Yeah.
Two like input image plus or two just layers. Then a max pooling, 3 layers, then a max pooling. When we do these two max pooling, we know which one we kept. For example, here. So this is, let's say, this is a slice of the max pooling. We know that for this 5, we took this value.
Yes.
For this 6, we know that we took this value.
Yes.
For this 7, we took this, and for this 8, we took this. We know this.
Yes.
And because for semantic segmentation, we have a symmetric network. This part has the same architecture as this part. It does just the opposite. So here we are detecting what complex shape we have, and here we are decoding it to know what pixels is, what every pixel is. So we have a symmetry here. So we know, so this layer, every layer has its counterpart layer. So for this layer this is its counterpart layer. This layer has this counterpart as a layer. Is it still fine?
Yes, yeah.
So when we do the max n pooling, the reverse one, because let's take this. Here we did the max pooling. We know exactly what value we kept. We kept this, and this. We know which one we kept from here.
Yes.
So when we do the max n pooling, this one is the smaller version here, coming from here, and we are trying to make it the bigger version here. And we know that here in its counterpart, the other half, we took this. So what we do with this one, we put it in its original position. Here. We don't put it here, we don't put it here, we don't put it here, we put it here. Because it came more or less from this position.
Yes.
But here, it goes back, and we put all zeros everywhere on the rest. Same for this 2. Where shall we put this 2? Here, here, or here, or here? We put it where it came from. It came from this.
Yeah, okay.
Here. And same for the others. And we put zeros everywhere. We don't know what to put. Is it clear now for the max and pooling?
Yeah, thank you, yeah.
The others, guys, is it clear? For the max and pooling? If you haven't attended the few previous sessions, you will struggle a little bit, but feel free to ask any question if you feel anything. There is another way that is more clever than the max and pooling, and what we call transpose convolution. Now the transpose convolution, it is a little bit, not really, but it's a little bit the reverse of the convolution. So what is the regular convolution is something like that. So we slide like here for this value, and we compute the convolution here. Same goes in here. Then we move a little bit with 1 pixel, side 1 and pad 1. We move a little bit here, and we put this value, and so on. So this is the regular convolution. Are you still with me?
Yes, yes.
So this is the regular convolution. When we use stride equal 2 and pad 1, it means that we move by 2 instead of moving by 1. So you can see instead of moving, the blue is not here. We are moving by 2. Of course, we get something smaller. We get something that is smaller. Are you still with me?
Yes.
We have less values. So what we want to do is the reverse of this. Like we have 4 values, and we want to make them more values. So we do what we call the transpose convolution. And it has also the stride and pads. So what is happening with transpose convolution? We do some padding depending on the strides and paths. So for example, here with stride equal 1, we do enough paddings to duplicate this. Every like cell will be twice itself. So we put some padding here. They are all zeros, and we do the normal convolution, as you can see. So here to get 4 by 4 from 2 by 2, we have to pad things by 2 in each we do a 2 padding. And when we do that, we do a 2 padding and we fill it with zeros, and we do the regular convolution, we end up with 4 things. So this pixel, this value that is here, is going to include all of this, and then all of this. So everyone is different. Every cell has different cells that are computing its value. So this is with stride equal 1. This is called transpose convolution. Another version with stride equal 2 and padding equal 1. Instead of putting the padding elsewhere, like in here, we do this padding. So we put zeros around with stride equal 1, padding stride equal 2, and padding equal 1. We put, when we have this padding, we put zeros around, and we compute the regular convolution, as you can see here. So from 9 values, like in here, we got how many? 5 by 5. From 3 by 3, we got 5 by 5. And there is a proper formula when we have stride and padding, a proper formula that tells you how many like zeros you fill in between, and how many zeros I haven't put it here, but I can send it to you, and how many zeros we put around, depending on how many strides we have and padding. And there is a proper formula to tell you that. So this is what we call the transpose convolution. Is it clear, or shall I repeat it?
Oh, it's clear for me.
Yeah, it's just a way of filling zeros around and applying convolutions, regular convolutions. So we can have bigger images or bigger activation maps. Like from here, with stride equal 1 and padding 0, we adjust things around with here, and we have multiple variations to have this. So this is the reverse. It's not really, it's false to call it reverse convolution. It's not really, it's still a convolution, as you can see, but we call it a transpose convolution. Okay? Are you happy, guys?
Yes.
Ali, Mus'ab, Salsabil, Hafida?
Yes, it's clear for me.
Perfect. And sorry again, guys, for not updating the calendar. I know it was confusing for today. Sorry again. So this is for semantic segmentation. Just a quick question. How would you approach an upsampling problem? For example, moving from a low resolution image to a higher resolution image. How would you do this? By using something like this transpose convolution or something like that. How would you do that? If you want to transform a film, you have a video, or just say an image, single image, and you want to move from its original size, 480p or something like that, to a 4K image. How would you put a model like that?
Like we need to take 1 pixel and divide it to more, like a projection of 1 pixel to higher.
Yes, but how would you do this? Do it like when you make it more. We need to make it intelligently more, and not just. There are ways.
Autoencoder.
Autoencoder is one form. This is like the architecture of the autoencoder is very close to this architecture, by the way. It's just the output is the same as the input that we are going to discuss. Yeah, or we can have some encoder where here we detect what objects we have, and then here instead of having the same size we are going to have a bigger size, and we train something that like encode the image, like in here, We detect what features it contains, the bigger features, and then the second part is not exactly the same, but it like upscale. It makes things bigger, and we go with something that is here. We produce a bigger image. This is more or less how. There are multiple ways of doing it, and it's still a research area. But this is like one way. Like we can use something like an autoencoder or semantic segmentation inspired model, but in the output, we don't have something similar, but something that is bigger. Here, so we add more layers here. This is one way of doing it. Is it clear?
Yes, yeah.
We have also what we call the skip connections, like in UNet. UNet is an architecture for semantic segmentation. A skip connection takes these features and add them here. It's like this layer will not only depend on the previous layer, a little bit like ResNet, what we saw with ResNet. This layer, it's not exactly that. With ResNet, we are doing a sum, but here we are just adding features, concatenation. So this layer will not depend only on this layer, but on this and the one that is symmetric to it. So it takes the two inputs, this one and this one. We call this skip connections. This layer also depends on this layer and this layer as well. So it has more information to produce something better, to decode the image. It's like this one is coding the image into what it contains, a compressed form of information, and this part is decoding the image. So it's good to have some extra information for some layers. For example, this layer takes this, and also this. Is it clear for the skip connection? No?
Rebecca, can you go through it again, please?
Yes, sure.
Thank you.
So normally, we have multiple layers here. In normal convolutional neural networks, each layer produce something, produce like a cube like this. And this will be the input to the other layer, to the next layer. Yes? Where we apply the convolution, etc.
Yes.
So each layer is going to produce some information like that, this. Is this fine?
Yes.
So when we have the skip connections, for example, here we are, this layer is going to produce something that will be fed to this layer. This is the normal architecture. Still fine.
Yes.
With the skip connection, this will take this layer, what is produced by this layer, and also what is produced by this layer. Normally, what is this pair is producing is going here. But with the skip connection, this layer will take this output and this output. It will take two. One normally this layer takes this. Sorry, this layer will take this output from here as an input, and also this. So it will take two sets of information. So it will take two cubes that are the same size. So with this one and this one. One is coming from here and one is coming from here. So it will be just be a bigger cube, something that is wider. Well, something that is wider. One is coming from the previous layer, which is normal, and one that is coming from like a layer that is symmetric to this one. That is doing some more or less something symmetrical to it. So it is taking just two sets of information. It is better. So it gets like two features. It can understand the image or the information better. It will do like a better job when it receives two sets of information. Is it clear enough or not yet?
Yes, yeah, thank you.
The others, guys, is it clear enough for you what is happening with the skip connections? So this layer, what is producing, is going here. And what this layer producing, and it's not just going here, but it will also be used for the decoding part. Same goes in here. It's just called the skip connection. because when we have like two information, it just improves the results. It's not mandatory. We can still have the normal architecture, but when we add it, we take this result and put it here. It just makes things better in terms of results. Are you happy so far? I know if you have missed some sessions, it can be a bit tough, but feel free like to ask any questions anyway. So this is for semantic segmentation. It's very simple. We can go deeper than that. One question. How would you evaluate the performance of semantic segmentation? One of the problems, guys, for example, here, let's take this example. One of the problems, say here, if you are trying to detect only cat and background, the background is a lot bigger than the cat. Yes or no? Is it fine? The background is bigger than the cat.
Yes.
Yes. Yes.
Yeah. So if you classify everything as background, how much accuracy will we get? Something like maybe, I don't know, 70%, 80%, which is not that useful. Everything is classified as background, which is completely false, and we got a score of 70 or 80%. So doing like things pixel-wise is not good, because where the background is huge and the model, if it struggles a little bit, we classify everything as background, and the score will be high. Do you see this problem? Can you see these problems, guys?
Yeah. Sorry, what problem right now?
Okay. Let's say that we are trying to detect if it is what is a cat and what is a background. Just two classes.
Yes.
We are trying to detect which one is what part is the cat, but the back and what part is the background. But the background is a lot bigger than the cat. We have more background than the cat.
Yes.
So if we classify everything as background, we still get a good score.
Yes, better than if we classify everything as cat.
Yeah, and it's still some bad results from like a logical point of view.
Yes.
We don't want everything to be classified as background or everything classified as cat. We want like to say this is the cat, and sometimes it's even worse. We can have an image like this, and the cat is very small, like in here. So the algorithm will probably classify everything as background, so it gets excellent results without trying to make efforts to classify what is a cat and what is a background. So this is a problem because we have an unbalanced data points here. Not data points, but like pixels. Things are imbalanced. For every image, things are very imbalanced. Like we have classes, like generally the useful classes are a minority, and the rest, that is the background, is most of the image. So like trying to look at every pixel and sum in which one is correct and which one is bad is not a good way to do things. Okay?
Yeah.
You agree with me, guys? Thank you. Amal, Farouk, Ali, Salsabil, what do you think? Mus'ab, Hafida, please. So we don't want to classify things by pixel or to rate every pixel separately. So what we do instead, what we call the mean intersection over union. So this is what it means, the mean intersection over union. So this is, let's say we have the cat class. So here we have the cat, and here this is the image. So we treat every class to like separately. So we have this cat, and we see what pixels we detected as cat from the original image. Here we have the original image, and here we have the model predicted. So we see the intersection. We look at the intersection. So this is an intersection. We divide it by the total size. So we get a percentage. So this is the intersection divided by the total size, divided by this. So if they are the same, exactly the same, we get 100%. If not, then we get a lower score. So we do this for like class-wise. We do this for the class, and we do the same thing for the background class. So we compute it for every class separately, and then we average them for the cat class and for the background class. So we average them. So this is a very simple way to compute performance. The intersection over union. So we do this for the class cat, and we divide it by the entire union, this plus this, and we get a score. So we do the same thing again for the class background, and we get a score. So it's like we make the class of cat and background the same. We give them the same weight, not by the number of pixels, but because they are two different classes, they just receive the same weight. Is it clear?
Reda,
Mm-hmm.
it's similar to object detection.
Exactly. Just not exactly similar, because in object detection we fix it. We fix what we are going to have a look at object detection. We fix what is the minimum intersection we want.
Okay.
But,
in this case, we have data sets with x and y.
X and Y,
X of y and y of object in image. We train it, and
for segmentation, for every pixel we know what it is. Every pixel is classified. It's like a matrix of classes.
Okay.
Every pixel has a number, which is the class. So we classify pixel wise.
Okay. It's like we have circle. We have a picture. We have a picture and a file with it where it define the places of the cats, for example.
Yeah, it can be anything in the original dataset, but you have to always convert it into something like this, like a matrix, and for each pixel you've got a class. So you've got this matrix.
Is it applicable? Is it possible to apply this on multi-object? Let's say a
multiple
picture
classes.
Yes.
Multiple classes, yes. You can apply it to multiple classes. However, well, we are going to look at that with the localization objects overlap. Here, they don't really overlap. And if you have here, for example, two cats, like this, we have a cat here and a cat here, the whole thing will look like one cat. You won't have like two separate cats. Like they are a little bit fused.
What if we have discontinuous object?
When they are discontinued, it's easier to add an algorithm that can detect how many cats we have. But yeah, when they are connected, it's not that easy to differentiate them. Which one is the first cat? Which one is the second cat? There are algorithms for that. There are algorithms that do the same thing, but combine localization and segmentation at the same time. Like yeah, it's one of them is the most famous one is not well. It's based on RCNN, but we are going to look at. It's called Mask RCNN. It was developed by Facebook.
Okay. What R stands for?
What is what?
RCNN, R, the first letter.
Oh, we are going to look at this. We are going to look at this algorithm. After this, we are going to look at object localization.
Okay, thank you, sir.
No problem. Any question, guys? Is it clear how we are measuring performance when an image is when we did a good job and when we did a bad job? Can you confirm, please? Mus'ab, Salsabil, Hafida.
Yes, Rida, you mean the answer to how we evaluate the performance?
Exactly, yeah.
Yes, yeah. So it's the intersection over union. It's just, this is what you were explaining, right? It's the solution.
Yes. Exactly. So now I hope it's fine how we are computing the performance. Can I move forward? Are you happy, Farouk, Ali, Salsabil? Please confirm for me, all of you guys.
Yes, that's fine. Yeah, thank you.
Yes, yes, yes.
Yes, Rida, fine. Thank you.
Great. Now, with object detection, I can give you an exercise later for object localization. But now for object detection. So what we are trying to do instead now is finding the bounding boxes. Finding the bounding boxes. So you can see the difference here. Previously, we detected the pixels, but here we are trying to find the bounding box. So we know in the semantic segmentation, sometimes it doesn't tell us how many objects we have. So let's say we have two cows, like this one and one just next to it. Semantic segmentation, what it's going to do is to give us like all the pixels that are cows. So we don't know how many cows we have. You can know by your eyes, but the model doesn't know. Is it clear, this problem?
Yes.
But for object detection, it is inferior in telling us how many, what pixel are what, but it tells us how many objects we have. So it tells us how many objects we have, but it doesn't tell us what pixel is what.
How?
Evaluation is this. Sorry?
How? Sorry.
Yeah, it's a different set of algorithms. We are going to have a look at that. We are going to have a look at a few of them. So we have this, for example, a cow here. What is a bit less accurate in object detection? It tells us how many objects we have, but it doesn't tell us exactly what pixels are. Instead, segmentation does that. There is another class of algorithm that combines both. But we are going to have a look at it later, or just to mention it. We don't really have time for it, but just to mention it. Well, for the evaluation, we do the same thing as intersection over union. However, we fix the threshold. We fix the threshold. So we take this IOU. Like for example, here, if IOU equals 0.5, which is 50%, it means that to take a case as correct, they need at least to like overlap at 50%. Like the ground truth, the original image, what is the object, and what we detected. So for example, this is correct. If here they are like this is not correct, because this is inferior to 50%. If we take 70%, like in here, we have like, we need a bigger intersection. 90% is even bigger. Like they almost overlap. So we have to fix it. Previously, it was just to detect this percentage meant the accuracy of the model or the performance of the model. But here we have to fix it and apply it to every object because we have multiple objects. So if, for example, we can have multiple cows. If we have multiple cows, we do the same thing for all the cows, and we compute how many objects we got accurately. If we use 50%, we count how many cows we got them at 50%. Like the bounding box was as close as what we had in the data set. So 50% is commonly chosen. It's commonly used. Okay, is it fine?
No. Sorry.
Yeah, go ahead and ask.
Okay. Thank you. Thanks, Hafida. So what was the percentage stand for?
Yeah, this percentage is we have a data set. The data set is just some images. Say we have animals here, and in this images we have the bounding boxes like this. Here, this is the data set. Okay.
Yeah.
And the model is trying to produce this. It's trying to detect what object do we have. It's trying to find the bounding boxes, where the box is. So to tell that this box was successfully found, we look at what the model did. We have this here as the box. So we look at what the model did, and we see the intersection of a union. For example, for this image, say the first bounding box was here, the original one, I mean the data set, the ground truth, and the other, what the model found is here. Is this a success or a failure?
Is a success because the common area has.
Yeah, but depending on what IOU we took. Depending on what IOU it took. If we took a 90%, it's probably a failure. 70%, probably a failure. 50% should be close to it.
Mm-hmm.
So we have to fix what IOU do we want to use. In that case, the smaller the IOU, the higher the accuracy or the performance we will get, because this one is easier than this one and easier than this one. So this is this IOU value means. So here it means that we have one success, say, and here we detected, for example, this, which is another success. In the third one, we got something like this, which is a failure. It's too different. So we got 2 cases out of 3. Okay?
Yes, yeah.
So here it's like this, here it's like this, and here it's too far, and here it's 0. So we got 2 cases correct out of 3 cases. Okay?
Yes.
All of you
Thank
guys? You. Is it fine?
Yeah, I only have one question. Why is L.5 most commonly used? Why not the higher, the more accurate?
I can't really answer this because I haven't seen all the cases, but in the literature we see it too often. It seems a good balance, but it's probably different from one case to another.
Okay.
Because we can never have a 100%. Even the ground truth is just a point of view. If we move it by one pixel, it's not a big difference. If we move things by 1 pixel or 2, so we need the tolerance. 50% sounds, seems good enough, but everyone is free to pick what he wants.
So precision is not very important here.
It could be important depending on the case. So it's probably up to what business case you want to achieve out of it, I would say.
Okay. So if it's cars in a highway, it's less important than recognition faces.
Oh yeah, possibly. Or if possibly if it is a car, it can be even different, where you can tolerate bigger, say, bounding box rather than smaller and missing some part, because when we detect a smaller bounding box, some part of the car are not detected and you can have a collision with it. But if you have, so it is like in these cases you might use something different than this, because there is a danger in under detected. You can over detect a little bit by a bigger margin, but it's small, yeah, margin. But under detecting can be dangerous. So there will be a different measure than the IOU. But in the literature, you will find this measure used a lot. If you look at papers, you will find 0.5, 0.7, you both used, and you see the results of both of them to compare different models with with your own model. So you can have multiple IOU and you see what is happening. Okay.
Yeah, Reda, can we go? Sorry. Yeah, can we go less than 50%, which is like 0.5?
Oh yeah, you can go beyond 50%, like here 70% or here 90%.
No, I mean less than 50%.
You can. Nobody will prevent you, but you have to just justify it, because lower than 50%, it starts becoming like a bit
very
far.
Small.
Yeah. Okay. Are you happy, guys?
Yes.
Great. So now let's have a look at some algorithms for object detection. These algorithms can be very deep, and they probably need one session each. So we're going to just have a quick look at how they work. So yeah, now first, before that, let's have a look at the difference between object detection and semantic segmentation. This is object detection. So we are having this. And in object detection, as you can see here, objects can overlap. So we knew that it's always like a bounding box. We know that the guy is here, and the sheep and the animals are here. Sheep and animals can overlap. For example, here we have the first one. Here we have the second one. Here it's more of a semantic segmentation, as you can see. But it's not really semantic segmentation, because the sheeps are of different colors. This is more of a combination of object detection and semantic segmentation. Semantic segmentation will give the sheep all the same color. So this one and this one will be barely like different. They look like the same one. And the guy and the dog will have a different color. So this is like a difference between object detection and semantic segmentation. The first problem with object detection in semantic segmentation, we wanted to predict a matrix. For each pixel, we produce a class. Is it fine? For each pixel, we produce its class. This is for semantic segmentation. Is it fine, guys? Tell me, please.
Yes.
For object detection, instead, now we are going to have, for every object, the class, which is a regular classification, class 1% like probability, class 2 probability, class 3 probability, and also the bounding box. We produce two things: the class, what is this, and the bounding box. The bounding box are the top left corner and the bottom right corner. These two pixels. So the neural network here is doing what we call a multitask classification, multitask problem, not classification. It has a part that is a classification and another part that is a regression. Do you agree with me here? Do you agree with me? We need to do both. Detect what the class is.
So each neuron will have how many output?
Each neuron has only one output. There is no like A regular neuron has only one output.
Okay, so the neuron of last layer of CNN has each one has one output here.
No, we could have. Not this, we are talking about the fully connected layer. So we have in the fully we have the CNN layers here, and then the fully connected layer. The fully connected layer is going to output here the probabilities, what class it is, like we used to do. Do you agree with me, guys?
Yeah, yeah.
So we output the probabilities. So if we have like four classes, we have 4 neurons, each one producing a probability with the softmax. But here we are not trying to detect only the class. We are also trying to detect the bounding box. What is, we detected the class, which is a normal classification problem, but we want to detect where we are. Where is my object? So we have also to have some neurons, some output neurons that produce values. Here we have 4 values. Every value is this top left corner has 2 values, and the bottom right corner has 2 values to draw the square or the rectangle. So you can see here, this problem is a classification or a regression in this top part.
Classification.
Exactly. And this, what is this?
Yeah, regression.
Exactly. We have a part that is a classification and a part that is a regression. What loss function did we use for classification, if you remember?
Softmax.
No, softmax is not a loss function.
Ah, loss.
Yeah. What did we use, if you remember?
Cross entropy.
Yeah, we use cross entropy. For classification, we generally use the cross entropy, the categorical or the binary cross entropy, and how many classes we have. And for regression, what did we say? We did it for deep learning regression classification or regression examples. For regression, we use generally the mean square error of or the absolute square error, or the mean absolute error. Sorry. So that's what we use for regression.
So what you are suggesting that we will have in the last connected layer, we will apply two loss
combination, a combination of loss functions. We are going to apply a combination of loss functions. A loss function that is applied here, and a loss function that is applied here.
So we will divide the output. We will divide the output and apply different.
It's at the end of the day, it's just one loss function, but it is built by combining 2 loss functions. This loss and this loss.
I see.
Because we have different, and there are other aspects of how to combine them, depending on the problem. But it is a combined loss function because we have a part that is classification and a part that is a regression.
Yeah, that's clear. Rita, I have a question that go back a little back, just about convolution. Convolution. When we converge when we extract features, we go vertically and horizontally, or just horizontally?
Both. Vertically and horizontally.
Both. Yeah. Okay.
In both directions.
Okay.
Yeah, it's. I think it is mentioned on the slides and the videos, the previous videos. Mm-hmm. So, are you happy with my explanation and why do we use a combined loss function? Amel, are you happy?
Yes. Yeah.
We use a combined loss function. Well, in terms of coding, it's not that much. You just have to specify it by one line of code, nothing much. Or sometimes you put your own loss function. But we need to know that in this case, we call this multitask learning. One part is produced, like we have 2 types of things that we are predicting. And it looks like a multitask learning problem where we have produce the class and another task that is the bounding box. So we have a more complex loss function. And it happens in complex problems. We generally have more complex loss functions. I can give you an example that you can play with when we have these kind of types of loss functions. But I want you to first be comfortable with. Sorry.
It would be good, yeah.
But first, you have to be more comfortable with the regular loss functions and doing examples with the regular ones. Then we can move on to the more complex ones. One other problem, if we do that, if we do this, the output of the neural network is fixed. We cannot have like multiple neurons depending on the case. Normally, when we build the neural network, the number of neurons at the last layer, or even in any layer, is fixed. It doesn't change over time. Do you agree with me, guys?
So what will happen to the number of layers?
It is fixed. It doesn't change. Once we build the network, we don't change the layers and the number of neurons.
Yes, yeah.
It's always fixed. Yeah. Once we do the training, etc., and we don't want to train further, things stay fixed. They don't change.
Yes.
So how many objects are we going to detect like when we do this? How many objects are we going to detect?
According the number of or classification, we will got correct.
Sorry, what?
According the number of classes we have.
But how many objects? Say we have 100 cows here, and here we have only like say we have 4 classes. So we have 4 neurons here, and 4 neurons here for the corners. Detect the corners. So how many cows are we able to detect?
4.
In one image.
If they are not overlapping, so we should detect all of them.
No. It doesn't matter if they overlap or not. We will detect only 1. Thank you.
Yeah. We
will detect only 1, because here it will tell us what class it is for only 1 sample. These are probabilities. And here, what do we have here for these 4 neurons? They will only detect 2 corners. This and this. They can detect multiple corners because we put the image here, and this is what we get. We get this and this. They can't get multiple corners. So we're detecting only 1. This is one of the first problem. Are you happy with this, Pharaoh?
In fact, no, because we will convolve.
Yes, but in the last layer, as you can see here, we are having fully connected layers. And this network is taking the whole image. It's not sliding. It's taking the whole image. This is a possible solution that you mentioned, Pharaoh. It is a possible solution where we convolve and we try to look at where we have a cow. It is possible to do that, but you will need to use this neural network multiple times. You need to slide, because the output will always give you 8 values. 8 values, just by definition, 8 values cannot encode like a bounding box for 100 objects. It is impossible.
Yes.
Yeah, 8 values cannot encode the information for 100 objects. They can encode things only for 1 object, because 4 are for the bounding box. Every bounding box requires 4, and the other 4s, the probabilities, are for one single label, 1 object. So the first problem here, if we use this kind of architecture, is that the number of objects that we have is going to be fixed. It's going to be fixed, like here. So there are several algorithms to tackle this problem. We have the first family, RCNN, fast RCNN, faster RCNN. These are like improvements over the other, and the mask RCNN that are like more or less belong to the same family. We have the YOLO. YOLO is very fast, and SSD. You look only once. They are faster. The YOLO and SSD are faster than the RCNN ones, but a little bit less accurate. And there are others that are less famous that we can find. So let's have a look at the RCNN family, region-based convolutional neural network. The first version was very slow. What we do what the idea that you mentioned, Pharaoh. What we do is that we produce region of interests. So we look at all the possible bounding boxes. And for each one of them, we put it in a convolutional neural network. It can be an SVM here or a fully connected layer. It doesn't really matter that much. So, but the problem here, can you notice a problem here? So for each region, we select a number of regions. We try to get the different regions of different size, and we look what we have inside with the convolutional network. We try to recognize it. Is it a dog? Is it a cow? Is it whatever? So, and the bounding box will be what we put inside, and it goes here. Can you notice any problem here? What's the problem here with this architecture, with this way of doing things?
But another network layer.
But what we are doing, well, it's the same network that is doing the recognition. It's trying to recognize dog or whatever. But what we are doing, we are calling it multiple times, too many times. And here the number of regions can be huge because we are just trying different regions. The number of regions that we are trying is huge. So, and we are calling this, like this convnet that we are trained multiple times, not by the number of possible or number of objects, but for every region that we suspect can represent an object. So this can be insanely slow. Do you agree with me?
Yeah, because the thing is, how do you suspect a region?
Yes, this is like the region proposal. It's another algorithm that I didn't want to go into the details. That will do the region proposal, and it can easily produce like 2,000 regions for a regular image, 2,000 different regions generally. And this is a lot, 2,000 calls to the convnet just to detect my objects. It can be very slow. We had after that another version, a faster version by the same authors. Fast RCNN. Instead of calling the convolutional neural network multiple times, depending on the regions, we use a convnet in the beginning. It can be an AlexNet, a VGG, a ResNet, all the models that we have seen before with transfer learning. So we use transfer learning to get what features do we have? What features we have at the end. So like we are using some transfer learning from these models. After that, we use the region proposal. We use the region of interest from this. So this way, we use the convnet only once instead of multiple times. And then the region proposal will try to detect the regions. And here we can get some probabilities with the softmax and with the bounding box. We can get that from the region proposal. So here we instead, it's like we are reversing. Instead of calling the convnet multiple times, we call it just one time, and the region proposal will work over the features of those detected by convnet. Do you see the difference, guys, between these two?
Yeah, but I don't see what has special. This convnet, what has special?
What's the difference? Here we are. It's just a speed. It's just a speed.
This convnet if we compare it to other CNN, what it has in plus?
Oh, it's a regular convnet. There is no problem. There's no special thing. But here, the region proposal now. So this convnet, there is no fully connected layer here. It just produces some features, some of these complex features. The last cube or activation map. And in the region proposal, we'll try to look at it and detect where do we have an object.
Okay.
It will look at it and see this rectangle contains an object. And then we have another CNN here that takes, this is a smaller one, that takes this and try to produce the bounding box and the classification. But it is a very small one. This one is very small. And it is a specialized one.
So all the smartness is in the region of interest.
There is a lot of work here. Yeah, we can have a look at it. It is sometimes we can use even fully connected layers or anything that can detect this region proposal. And this CNN will get the region, the small crop, and to give us what object it is and the bounding box. But this one is smaller than this one. It's a lot smaller because most things are computed here only once, and this one is a very small. So here, so what is really happening here is things that are common between this, and this are going before, and they are computed only once. So we, instead of computing these things multiple times, so we compute them only once in the beginning, and after the region proposal is applied, we compute only few extra layers that will give us the region and what object it is. Are you happy with the explanation, Amal? Please, Salsabil, please. You haven't talked too much today. Happy that you are talking, but please tell me, guys. I want you. It's not. I know it's not easy, so you have to tell me. I need some feedback from you. Nothing. I have a feeling that it is not clear yet, but I need to pinpoint where it is not.
Rida,
Mm-hmm.
in such problems, we just put images and detect objects, or
of course, we just feed the image in my model, and then we get the objects.
We don't need X and Y of objects.
What do you mean by we don't need them? Of course, when feeding the image, there is no X and Y when we feed the image. The X and Y are either in the set or they are produced. If they are not there, it means that we want to know where the objects are.
Yes.
So X and Y are not fed. They are at the end.
They will be discovered.
They will be discovered. Yeah, if we are training, we use them to train. If we are doing the prediction, if we are predicting, then they will be discovered, as you said.
In which step we found this access?
Of course, they will be at the end, the end of the network. At the end, we get what object it is, cow or whatever, and the box. So this is our goal. Our goal is to detect what is this and where is this. The location and the class, as you said, as we mentioned before. Okay, guys, Amal, are you happy? Tell me, please, guys. Hafid, I wanted to say something. I need you to get more engaged, please.
Yeah, it's clear. It's a bit complex, but it's clear.
Yeah,
I agree.
You see the difference. It's like because the convolution can be similar especially in the first steps. So what we did is to do this convolution only once, and then to do the region proposal, and then the rest of the convolution. After this, the fully connected layer will detect the location and the class for every object. Is it fine?
Yes, for me.
Perfect. And this way we were able like to make things a lot faster. If you want to know more, because I haven't put a lot of details here, you have to look at the algorithm of the region proposal and how it works to get the probabilities that a particular zone may contain an object. So this is for the RCNN family. Then we had another version, a faster one. It is even called faster RCNN. I just want to mention it. With faster RCNN, the region proposal is a neural network like. So we have a CNN here over the image. It detects the features or the features. Then we have a region proposal that detects the bounding box. It is just a neural network. And then a layer that detects the class and the bounding box from here. The region proposal is like fused. It's fused in with the network, with the CNN. Just one network it is made. It is more complex than that. We don't have time like to go deeply on the faster RCNN, but just to see the difference is that the region proposal is another neural network that is connected to the CNN, and it produces different bounding box for regression and classification. This is its output. So these are kind of algorithms. This RCNN family can detect almost an infinity of objects. Do you agree with me? Just to make it simple, let's go back to the original version. This is simpler. This is simpler. Let's go back to this original version. Others are just improvements for speed.
I have a question.
Mm-hmm.
I'm sorry. I have a question. Before entering to the CNN, we said that our problem is that the number of given the number of neuron, the number of image is to be detected is fixed.
The number of objects in the first architectures that we saw in the first place. Yeah.
Yeah. So here how many numbers?
It is unlimited because we have the number of region proposal can be infinite, and we are applying CNNs at multiple times. So we can have multiple objects. There is no limit.
But at the end, how many in the last layer? How many neurons we have?
No, we are applying. Let's focus only on this. This is simpler. On this.
Yeah.
Here we have the same thing that we mentioned before. Here it is set in SVM, but let's say it is normal. 4 neurons for the class, 4 neurons for the localization.
Okay.
We have this. So here we are able to detect only one object.
Mm-hmm.
But the region proposal is doing multiple rectangles.
Mm-hmm.
So we are applying this CNN multiple times. That's why the region proposal is the one that limits how many objects we are going to detect.
Okay, here it's clear. And for the other one?
The other one is the same, but it's just speed-wise improvement. We just put the region proposal here after the convnet. So we still can, the region proposal can suggest multiple regions. There is no problem with it.
Okay.
And we are applying a lighter CNN to it, to each region. So we can still have multiple, it's like what Farouk said, we are sliding, but we are sliding in a different way.
So if suppose the region proposal propose us 10 region, we will have 10 output, 10 multiplied by 8, by 8.
Exactly. Yeah. Perfect. Exactly. That's the number of outputs depend on the mood, if you prefer, of the region proposal algorithm.
Okay.
And how many regions we have. If it is 100, we are going to get at the a maximum of 100 objects. We can have less because sometimes it's the region doesn't contain anything. It's just a guess. The region proposal is just guessing where we can have an object. And this one will make sure that to detect if we have or not. Is it fine, guys? Thank you, Nessim. That was a very nice question, very pertinent one. Are you happy so far, guys?
Yes.
Perfect.
Yeah, thank you.
Perfect. Please stop me, guys. If you have any problem, stop me. Faster RCNN is just another improvement over speed. We have another one that is a lot faster than the CNN family, including the faster RCNN, but it has one drawback, but it is fine, still fine. It is called the YOLO. You look only once. It uses this only one CNN and only one. That's why it is super fast. For example, what it does, we have an image here. We divide it into regions, squares like this. So we split it. And for each cell, we have multiple cells. For each cell, we predict B boxes, fixed B. B is a fixed number, say 2, for example. So for each box, we try to detect 2 boxes, only 2. For example, here, this one and this one. 2 possible. So each box will contain a maximum of 2 objects. And what we do it for every box. For every box, we try to detect 2 objects, a maximum of 2 objects. Here, here, here. So here, how many we have? How many boxes we have? 3, 3, 7. 7 by 7, 49 boxes. So how many objects can we have? We will have 98. 98 objects we can have here. Different objects. So what we do this, we run this for every cell. Then we end up with something like this, because 98 like a bounding box is a lot. So we end up with something like this. This is a problem. Do you have any comment to make on this image?
Well, you said that we divide only, we detect only in squares.
Yes, we have multiple squares.
Yeah, but here we see a bigger square.
Perfect. Good question. Thank you, Nassim. That's an excellent question. We are seeing a bigger square. Why? It's because when we say for every square we detect 2 different bounding box, it doesn't mean that it should be inside. The center of the square should be inside. For example, here, the center is inside, but the rectangle can have any size. So we can have 2 center of the rectangle. For example, here and here. Does it answer your question, Nassim? It's just the center of the rectangle that is inside the square. But what we are trying to predict is that every square, every rectangle can go beyond. So for this rectangle, for example, we will have only 2 centers. For example, here and here. And the size can be anything. It can even be here, like this. So this way, we are just limiting the number of segments or the number of rectangles that we are able to detect. Here, how many we can detect? 98. It's 98 segments or 98 rectangle bounding box. Does it answer your question, Nassim, or not yet?
To be honest, it's not a simple algorithm. I think it's
yes.
It looks really complex.
It's not that. It's still just a CNN, just a simple CNN. It's exactly like the algorithm that we mentioned before with some variations. Not the RCNN, the one that I mentioned before, and I said that there is a problem with the number of objects we can detect. So we divide
for example,
image.
Here it's For example, here we don't say why just 2.
No, it's just a number that we pick. B equal to is used frequently, and you can use any number. You can use 1 or 100 if you prefer. So when we choose 2, it means that for every cell, we have a maximum of 2 objects in every cell when we pick B equal to. So we have a maximum of 2 objects per cell. But the object, the size of the object can go beyond the cell. It's just the center of the object is inside the cell. For example, this car will probably belong to this cell because its center is here. So we say that this car is inside this cell. The size can go beyond, can be like the boundary box is like this. But because the center is inside this cell, we just say that this car is inside this cell. We are focusing on the center. This is just one way of telling how many objects we have, a maximum of objects we have in this image. So in this case it's 98. Is it clear?
We still don't know how it solves the problem of the output.
Not yet. I'm coming to that.
Yeah. Okay.
Is it clear for you guys? Amal, please. You guys, Hafida?
Yes.
Yeah, it's clear for me.
Yeah, for every object we have B number, for every cell we have B number of objects. Then, so does this explain this, what is happening here?
Yeah.
This is now clear what these squares mean or these rectangles mean.
Yeah.
Amal, Hafida, Farouk, are you happy? All of you guys?
Yeah, it's clear
Yeah,
now.
thank you.
You
Yes.
remove the
Now we need to do, well, first there is this simple thing. Boxes with low probabilities of containing an object will be ignored. So we put a threshold. So we have 2 boxes for each cell, and we have a probability. They have probability that they contain an object or not. We produce a probability. The network is going to tell how likely that there is an object there. So with low probabilities, we reduce them. We remove them. Say a probability of 50%, of less than 50%, of any object, any square or rectangle with a probability of less than 50% containing an object will be ignored. So we remove a number of squares or rectangles. This is the first step, which is simple. Are you still with me?
Yes.
Are you still with me, guys? Amal?
Sarada,
Great. All of you guys, please stop me here. So we have
Why-
squares.
Why it doesn't Rokoni? No, Rokoni, the tree.
It's just not in the database. It's just not in the data set. That's all.
Okay.
We are not trying to recognize trees. We don't have this in the data set. We are just trying to recognize the dog, the bike, and the car. It's not a problem. So we remove, for example, here, this square here, or this rectangle here. It doesn't contain anything. So the probability will be very low for it containing something. So we remove it. We keep only rectangles with high probabilities. So this image will be simpler. Then the other clever part that we use is that we run what we call the non-maximum suppression. I'm going to explain what it is. After running the non-maximum suppression, we get this. Why do we run what we call the non-maximum suppression? For example, this car have like this bounding box, and it belongs to this square. It is possible that the model will say, well, we have this car belonging to this square with this bounding box. And it will tell we have another bounding box belonging to this square, and it looks like this. Belonging to this square, because in the middle is here. Say this is. They are more or less both correct. They are both correct. Yes or no?
Yes.
But they represent the same object. We should keep only one. We should keep only one. Yes or no?
Yes.
Yeah.
So if we want to keep only one, we need to do some trick. And this trick is called the non-maximum suppression. When two segments or two rectangles or bounding boxes overlap with each other, we compute the overlapping region. If it is higher than a threshold, it means, and they represent the same class, it means we have to keep only one of them. So we look at the probability. Which one has a high probability of containing an object? This one has a higher probability. This one has a higher probability than this one. For both containing an object and what probability of that object is. This will probably have a higher probability that this is a car because it contains all the car. And this one contains less than the car. So its probability containing the car, this one will be lower because the bigger image will probably give a higher probability. Are you with me? Do you agree with this?
Yes, yeah.
So, yeah,
sorry, and we do the same with the 98
exactly
bounding boxes.
Exactly. We look at every bounding box that overlap with another one. If they produce the same class, car, or dog, we keep only one of them. The one that has a higher probability for and the confidence for the class. So this one is better. So we keep only one, only this. That's why when we run this non-maximum suppression, we end up with only this. But as you can see, Nassim, the YOLO is still limited on the number of objects we can detect. Yes or no? We cannot detect an infinity number of objects. It is subject to B, to the value picked for B. Yes?
For the moment, you give us, I would say, the big picture of how it works, but we don't have detail. So we don't know how it solves the number of
the YOLO is limited on the number of objects it can detect per image. It cannot detect an infinity like the RCNN. It cannot detect an infinity number of objects.
So sorry, Rida, so we are the one who fix the number of objects that YOLO has to detect? Okay.
Yeah, we have to pick a B.
Okay.
Yeah.
So that
What
means
about
if you want like 4, in this case, it will detect the 3 if fixed for 4, for example.
Sorry, I couldn't hear you well. Sorry. Can you repeat, please?
I'm telling you, like, for example, if we fix the number of objects for YOLO here in this example at 4, it means it will detect, for example, the 3 as well.
Not necessarily. Well, here we fixed it to 96.
Okay.
96 possible because we divided it into cells. We had 7 by 7 cells, which is 49 cells, and we said that B equals 2.
Okay.
So the number of bounding boxes we are trying to detect is 92 multiplied by 49 multiplied by 2.
I see, okay.
Which is 98 possible segments. What is the YOLO they're doing? Its output is 98 multiplied by 8, actually, or the number of classes. So the tree was not in the data set, that's all.
I see.
The tree was not learned in the data set. We were just trying to detect car, bike, or bicycle, and dog.
Rida, let's say if we had small ball in the image, would it be a problem for YOLO to detect?
More what?
Like small object, like a ball or something.
It depends on the data set. If the data set contains small objects, then the YOLO should cope with it. But if the data set, the original data set doesn't contain it, then the YOLO will probably struggle with it. That's what I would say. Yeah, and smaller, well, it can have another influence when they are too small. But yeah, I think that it would be down to the data set. If the YOLO was trained recognizing small objects, it can cope with them. But if it wasn't, then
my thinking is that if we have like a small object, it might be bounding box.
Yeah, well, it's still down to the data set. If you're in your data set, the YOLO was trained with small enough objects, then it will probably be able to cope with them when we do the prediction. Yeah, and if in the dataset we don't have small objects, for example, the cars were all that of this size, and then we get a car of this size, probably the YOLO will not detect it.
Okay, yeah, thank you.
Are you happy with this, guys? Still, the YOLO has a limit on the number of objects it can recognize, but it can be a very big limit. You can set it by this number. And it's actually looking at the center of the objects. It's scanning the image by trying to find if a zone contains the center of an object. That's what it is doing. I try to look at all the image by looking at if we have a center by looking from that cell, can we detect an object? And when we look at here, can we detect an object? And it worked well. RCNN is generally better in terms of results, but YOLO is much faster. Because as you can see with YOLO, we have only one convolutional neural network where the whole image is firing and producing the bounding boxes. And so at the end of the YOLO, we have multiple. We have 98 multiplied by 8 or something outputs. For each zone that the YOLO is able to detect, we have some outputs. I know it's a little bit complex. You need really to get more familiar with the CNN and these things. I wanted here to just give you an overview of these algorithms and how they work. It's not enough to have just one session about them. But can you feel what they do?
To me, it's clear, given that the output is 98 per 8.
Yeah, but the output is fixed in the YOLO. The output is always fixed.
Yeah.
And then we have the non-maximum suppression and the low confidence zone detection that will come after the neural network and do the filtering, remove some things, etc. So that's an extra layer, not layer, but an extra algorithm that will do this reduction to this. So can you feel how they work, guys?
Yes,
Because,
yeah.
Yeah, it's normal that you will struggle a little bit. Now we started to touch more complex topics, not regular convolutional neural networks, but things that are a little bit more complex. That's why you will feel struggling a little bit, but that's fine. That's completely fine that you struggle with these things at this level. I think most people do.
To me, it's
really almost everybody.
Rida,
Mhm.
in this case, how can we calculate the performance of this model?
Same as before. At the end, you get this result. You get this. In the data set, you have the ground truth. You have the real bounding boxes. You have the real bounding boxes here, here, and here. And you do the intersection of the union. So in the data set, this is the dog. In the data set, let's say this was the dog, a bit smaller. So the intersection is this zone. Is here. Yes or no? This is the intersection.
Yes, it is.
So we take this surface and we divide it by the sum or the union, this surface. All of this. So we use this. Sorry, it's not. What am I am saying? Sorry, I made a mistake. It's not that. Once we do that, it's not enough. Once we do that, we have to, of course, we have to pick the intersection of the union rate over union, intersection over union rate. Is it 50%? Is it 70% or 90% or something like that? So if it is 50%, we take this as a success. If it's 90%, it will probably be a failure, not a success. And we compute how many cases are successful for this image, divided by the total cases. Is it fine? Ali?
I don't understand the probability of union, you said?
The intersection of union. It's how, like, if we to take like a case as a success. For example, this dog was successful to be recognized. What we do, we take the ground truth is this red square. What the model detected was this. So we see what is the intersection between the two. This is the intersection. Yes or no? And we divide it by the union. The union is this. Is the pixel that belongs to this and this. So this is the union.
But I thought, but this is not a neural. Normally, it's the neural network who do this job.
Yeah, but the question I asked is how to evaluate this. Are we doing a good job or a bad job? So we do the intersection of the union. We have to pick 50, 70, or 90. So if we pick 50, this will be probably a success. It looks like over 50% good. If you pick 90, it will probably be a failure. So what you pick, it's up to you, as we mentioned before. Are you happy with this, guys? Amal?
Yes, yeah. Thank you.
So we choose yeah.
So it's always intersection over union for accuracy assessment and all these methods. Like we can't
Generally,
use
yes.
recall and precision and like true positive.
But if you use recall, you still use recall, precision, F-score, etc. per class. You can still use that. You're going to still use it. But when do you say that this is a successful case? One case. Recall, precision, etc. are going to depend on the number of success and the number of failures. True, negative, false, negative, true, positive, false, negative. Yeah. We are going to compute all of this. But when do we say that this is a true positive? We have to have a rate. Is this case? Yeah, because it's not binary. We need to make it binary. It's not true or false here. It is a rate of success. So when do we say we are successful or not? So we have to pick a rate, a number. And then after this, we can compute the F-score, etc. Even the confusion matrix, whatever we want to use. Okay? The accuracy, even like how many cases we got accurate. It's like the limit. When do we consider that a case was successful or not? One case. What is the limit? What is the threshold? Okay.
Okay.
Are you happy, guys? Please tell me.
Yes.
Yes.
These are some open source tools that you can use. They are very easy to use. If you have a look at the source code, you have your data set, and you select what algorithm you want to use: faster RCNN, SSD, RFCN, mask RCNN, whatever, and you get the training and the fine tuning on it, and you get your results. We have this TensorFlow detection API. It is open source, or Detectron too. It is based on PyTorch, and you can use that, and you get with very little coding, you get your results. Okay. I know I'm going a little bit too fast, but because it's the last session, I want to just to complete it. And I'm sure that you are going to need to have a look at these slides and even try different things later. It's not easy to understand all of these things at once, not for sure.
What do you mean last session we want you for RNN?
Not yet. We said that we are going to pause these sessions. I give you some more exercises. The 2 exercises I gave you before, plus 2 others. Mm-hmm. You get familiar with this more. You train. You try to the different things. Once you feel good and you can move forward, then we put other sessions for the NLP part, for RNNs, LSTM, the transformer, BERT, etc. Because they are a little bit more complex, and I don't want you to feel overwhelmed with all of these things. I want you to feel confident with
we will go
CNNs. Mm-hmm.
You will go for genetic algorithm or not?
No, we don't. It's not really a part of. Like, it's not a strong part of deep learning. I can give you resources for it. It's not. They are not that complex. I can give you resources, but they are not really used a lot in deep learning. They are used for optimization in deep learning sometimes, but it's not like a core topic.
Okay. Okay.
So I will invite you to have a look at this, run some examples. I will give you an exercise on using this, and they are very easy to use. This detectron, you don't need to code a lot, or TensorFlow detection API. It's just like you have TensorFlow that we used it last time, but you have something that wraps it to make things easier to use with these algorithms.
Do you have preference between PyTorch and TensorFlow?
Not really. They are both very good and used a lot. Use whatever you fancy.
Okay.
Our examples are in Keras and TensorFlow, but if you want to use PyTorch, it's totally fine. Also, MaskRCN, and I want to mention this to close this part. We are almost we're about to finish, guys. MaskRCN, what it does this. It's a combination of object detection and semantic segmentation. It will detect the pixels of the object and divide them. And like it will tell you this, we have an object here, and it will tell you what pixels belong to it. This is MaskRCN. For example, in the regular segmentation, we might have this as one single object. They will look like the same because they are both sheets. They will look like the same, but MaskRCN combines both words, object detection and pixel segmentation, or semantic segmentation. So this sheet will be separate than this, and we will have like them both differentiated, which is quite good. And you can use it easily with the Detectron or TensorFlow detection API. You just select it, you give it your data set, and you leave the training doing its fine tuning, and you get the model.
But we don't see yellow in there is yellow in TensorFlow.
There is YOLO, of course. There is the multiple. TensorFlow detection API has YOLO, has SSD, has a lot. I just didn't mention everything. And same for detection.
Okay.
Detection is also quite good.
Yeah.
It is from Facebook, which is normal. This is from TensorFlow. So here we close. I know I went very fast. If you feel that you haven't absorbed everything, it's completely fine. It's just that we don't have time to normally we would do these sessions, this detection in like 3-4 sessions, but this is quite a lot. I want you to first get familiar, and then we can expand more. I will give you a little pause, 5 minutes, and we go quickly to autoencoders, and this is just a quick overview, and generative models. I just want to mention them, and we will be done. So have a quick pause of 5 minutes and come back, please, guys.
Nice, thank you.
This conference will now be recorded.
So autoencoders, just a quick overview about them. How they work. So you have a regular neural network, like this one. Or let's see this. A regular neural network that is like that's the fully connected layer, the fully connected neural network, the regular one that we have seen before. It is encoded in that way. So here you have the input, and then we have a little bit less input, the neurons, then even less. And then we have like this symmetry in autoencoder. We have this symmetry here, a little bit like what we were doing, with semantic segmentation. But here, the network, it takes an example and it tries to reconstruct it. So let's say we are taking an image here. It can be an image or anything, an image here. And we are trying to reconstruct the same image. You're going to tell me why. Why do we bother? Why would we bother, guys?
To remove anomalies.
Possibly. We can remove certain things, but it's not only the case. Sometimes we want to produce exactly the same image.
To check if our feature detection is good. To check
you are close.
that.
You
are close
to check
to
that.
it. It's because one of the reasons we are shrinking. We are shrinking the representation. Here we had like a vector of 784 units. It could be more. Then we have only 100 neurons, which means every neuron will produce only one thing, one value. So here we went down. Then we went even down. We went from this to this. From 784 to only 20. And then started to do the opposite. In the network, the autoencoder is able to reproduce this from this. Is able to take these 20 elements and make them 784. The same as here, exactly the same. What does it mean?
We eliminate the extra information we don't need.
Exactly. So we compressed the information successfully. It means that we kept only the meaningful information here. Thank you, Farouk. We kept only the meaningful information here. We were able to go from 784 to only 20. And this 20 contain all the information required, the same amount of information in this 784. So what happened in this bit? We encoded the information, and here we decoded it. This part is the input, we encoded it, and here the reconstruction decoded it. And this 20 elements seems enough to represent this 784. Sometimes we lose a little bit here. We don't get it exactly the same, but we have a rate. If it is close enough, it could be fine. So we say that we have a good encoder. What kind of machine learning algorithm is similar to this? A non-deep learning algorithm. What kind of machine learning algorithm is similar to this? By the way, this is unsupervised. We don't have a class. Yes or no?
Yes.
Yeah, we don't. It is unsupervised. We don't have any class here. Just an input and an output. So what kind of algorithm we have seen before that does something similar?
PCA.
Thank you. PCA, exactly. The PCA, this is just a dimension reduction. A dimensionality reduction, what is happening here, without losing the information. If the autoencoder is able to reconstruct it, it means we reduce the dimension, compressed it or reduce the dimension, yet keeping the information. The PCA did something similar. We went to a smaller dimension, but we kept most variance. The variance was kept to the maximum. So the information is there, but with less dimensions. Okay? What do you say, guys? I want you to comment a little bit. Amber, we wanted to say something?
Yes, I would. I was going to say, yeah, they both have restriction of dimensions. So yeah,
they reduce the
reminds
dimension.
them.
Yeah.
Yeah.
Exactly. One good surprise. Are you guys all happy, guys? Please tell me.
Yeah.
Sabine, you like the PCA a lot. Are you happy?
Yes, I am. Thank you, Rado.
Perfect. Then what we can find is that when we do this thing, when we do something like this, an autoencoder of this size, just one hidden layer here, single one, and then we try to transform again to the original dimension. What we find when we do this like encoding this compressed information, we found out that it looks a lot like the PCA. What the PCA produce is very similar to what an autoencoder of one hidden layer produces. That was a clear observation in many cases. When we have more, we have a better representation. When we have more layers, of course. But with one single layer, it is equivalent, more or less, to the PCA. Okay? Still happy so far?
Yes, yeah.
So this is the difference between the autoencoder and the PCA. Can we get an inspiration now by autoencoders, for example, to detect if an object is the rotation of another object? Say, we have an image that is a triangle. Another one has a square. And another one has a, I don't know, a car. We have something like this, and we have something like this. We want to create a model that will tell us if these two are the same object but with a rotation, and these two, if they are the same object with a rotation, but this and this are not. How do we do that? This is now a little bit of an advanced topics in deep learning, but you should be able to cope with them. How do we do that? Like, we want to know if this and this are the same object but rotated. How do you do it? By the way,
maybe we can.
Yeah.
In addition to convolve the features, we rotate them with many angles.
So you try multiple angles and you see if they are the same. If you do that, you don't need deep learning at all.
No,
I guess
I said, as we did for the convolve, we move horizontally and vertically. In addition, we add the inclination.
Rotation. Yeah, you can do that. You can do that. It's fine. But even convolution is not required, because when you rotate, you superpose them by a way, and you try to compute if they are close to each other or not, pixel-wise. It is possible to do that. But I want you to find me a solution with an inspiration from autoencoders. It's not exactly autoencoders that will be used, but something similar.
I guess we rebuilt one of both image. One of this image.
Yes, you are close. You are close. What we want to do, we put some
autoencoder.
Some autoencoder like this. Here we have the encoding layer. Here we have the input. An autoencoder can have some convolution layer in the beginning. It's fine. Just like what we use in semantic segmentation. We can have anything here. And here we have a small layer. And same here. What we want is this encoding layer is to be able to produce the same encoding for a triangle that is rotated. So if we keep rotating, it will always be the same encoding here. We can do that. It's a little bit of advanced topics, but we can still do that. If we rotate it here, the encoding will always be the same. This will be great, don't you think, guys?
Actually, I still didn't understand what is this autoencoder. Is
it
just
compress the information? We contain the information, the meaningful information of this, for example, a triangle or something. We'll just compress it, a dimensionality reduction, but we keep only what we need. So we need an autoencoder that is able to encode this and this the same way, or almost. It will contain the information for this triangle and this triangle here, exactly the same information, the same values. If we can do that, we just need to compare them. We just need to compare this encoding and this. And we don't need to rotate or do anything. We put the triangle here. We get the vector, the compressed vector, and we compare them. If they are the same, it's fine. There are ways of training this kind of problems. I'm not going to tell you that now. I think it's too much. I just wanted to mention this encoding for you, so we can control how do we encode things. I just wanted to mention this information. If we want, we can have a session about it, how to do it, but I think it's not for now. First, I want you to train on regular stuff that we did so far. After that, we can go to the more advanced topics. Any questions, guys?
If I understand, you want what you mean. You mean that we add smartness to the encoder to encode different same form with different rotation to a single one chain.
Yes. Yeah, it will be encoded the same way. Whether it doesn't, it's like rotation invariant, we call it.
Okay. Okay.
So rotation invariant. Same goes, for example, this kind of problems can be used with signatures. Signatures have a lot of variant, something like this, something like this, something, and even your signature is always a little bit different. Yes, don't you think?
Yeah.
So we can encode the signature in a vector in a way that most signatures, like the same signature, will be the same, whether rotated a little bit, whether well, signature can always be rotated. You can sign it in any way, or slightly different. So their encoding, the same signature, will have a similar encoding. And we just compare the encoding to determine if it is the same signature or not. Because comparing signature can be not an easy task. So this encoding is a very powerful tool if we know how to influence it. It's like what aspects of things we want to keep in this encoding. And there are multiple ways. For example, if we want rotation to be the same, what we do, we put this triangle here and this triangle here. The loss function will assess how different this encoding for this triangle and this are. If the loss determines that they are too different, then the network will be updated by a lot. If they are very small, the network will be updated by a small thing, by very little. The loss function will be the difference between this encoding and this encoding. We want this encoding to be as close as possible. Can you picture it in your head? You don't need to necessarily understand it fully, but just to did you develop a feeling about it, how it works? Please tell me, please. I know it's not easy, but that's I just want you to have a feeling about it.
But Reda, I have a question here. How we know? I'm talking about the middle layer. The middle layer is like a little bit difficult
the size.
Yeah.
Good question. Thank you, Farouk. Excellent question. Yeah, you have no way to determine the optimal size in the beginning. In my knowledge, you have to try different sizes and see. So, it depends on the problem, and it's very hard to determine the minimum. We need the minimum size. It's very good to have it very small as possible. So you try with small size and you see, and you keep increasing it a little bit, and you see if you are getting good results. Does it answer your question?
So far. So we have to try.
Yeah, we have to try, and the smaller it is, the better. We want it to be as small as possible, because the smaller it is, the less unuseful information will be in. We try to keep only the useful information, and by that we try to make it as small as possible. Okay?
Okay.
Thank you, guys. Now quickly, I want to go to, I know it's a lot, but I just want you to know that they exist. It's not something that you need to understand fully for now. It's just not non-realistic to understand all of these things at once. It's just good to know that they exist. Now, I just want to mention generative models. We are not going to go any deep on this. They are super complex, and it's just a whole topic on its own. So we have generative models, which means that we get something as an input, and we get another object as an output. For example, the super resolution. We have the original image, and we try to make it at a higher resolution. For example, this one, original, and we have this algorithm, this model, SR GAN, and you can see it is better, don't you see? It is better than this. This is a traditional method by cubic. It is not a deep learning method to create a super resolution. This is bigger than this one, but you can see the bicubic is it's not that useful. It's not that good. This is not a deep learning method. It's an old one. And this is one method as SR ResNet. You can see the name ResNet. It is using ResNet internally. And SR GAN, you can see it is even better. You can see this resolution. It is even better than the original. It's very powerful, don't you think? These are called generative models. They take this input and produce a bigger image as an output. So how they work? Another example of generative models. For example, we have this drawing or some segments, and we have the opposite. Here we have this street scenes. We have the real street. Here here it's just labels, as you can see. This color means it is a label. We are labeling each pixel. Road, car. So it's like each pixel is it's like the opposite of segmentation. Exactly the opposite of segmentation. So each pixel has a class, and we are doing the opposite with generative models. You can see it's insanely powerful. And we have a scene that looks realistic, more or less realistic. An aerial view. We have this input, and we get this, where are the streets and where are the buildings. This also this, and we get a night view at night, how it looks like. This is also some segments, labels. This is wall, this is window, etc. And we get this. It's super powerful. You can even draw something, as you can see here. You can draw this bag. I know. I'm sure one of you want to have this bag, and maybe Amal or Miriam or one of you. but you can draw it by hand, and you can have it in almost real shape, even with the shadow or the reflection. So these are called generative models. They are super powerful.
Rida.
Yeah. Yes.
How can we detect if the image is true or fake?
That's another story. It's a huge research topic that is being applied to text, being applied to this. It's I don't have like a quick answer, and I don't think that a quick answer exists. There are ways of determining the probability distribution of doing certain things, but I'm not an expert on how to detect these things. There are ways of detecting how predictable it is. If it is too predictable, like the next pixel is too predictable, it might mean that it is a fake one, but it is a huge topic and a hot one. Because a model can have like can be predictable in generating these pixels. But for example, noise is very minimal. We don't have enough noise like in real life pictures. There are certain aspects that we can use, but it's still not an easy task. We have also this to go from black and white to color. So your old pictures. Well, I don't think you have all the pictures that are like this, but your family pictures, for example, your great grandparent or some ancestor, you can have their image converted into a colorful image, which can be very interesting. So this is the power of generative models. How they work, I just want to mention how they work. We're not going to go deeply there. How they work is that first we build what we call a discriminator. The discriminator is a regular model, whether it's CNN or like a regular fully connected neural network or whatever. It takes an input, say an image, for example, and it tells you if it is real enough or fake. Real or fake doesn't mean that it is generated or not. It means that it contains something realistic. For example, a face is like that. Sorry for my drawing, it's so horrible. A face is like that. This cannot be a face. It's like the nose is in the top. This is not a face.
It's a pumpkin.
No, it's still a face, but a fake one. The nose is in the top. Like it's not a real face. Here it is acceptable as a face, but not this one. The nose is here, it's not real. So the discriminator is a model trained to recognize if something is real or not real. For example, this one is real, this one is not real. So it needs to, it's like a teacher that gives a mark. If something looks good, it gives it a 1. If something doesn't look good, it gives it a 0. It needs to be trained on a data set of fake and real images. This is the first part, called the discriminator. It's like a teacher. And then the generator. The generator looks like a model like what we use for semantic segmentation or autoencoder, something that is combined between the two. And what it does, it gets some noise as an input, a vector or whatever, and produces our image, an image. It can be an original image or something, but at the end, it produces some image, generated image. And the discriminator will tell it if it is good or bad. And this one will learn from this. So we don't have a data set. Data doesn't exist ready. It is like this produce something, an image, feed it here, it feeds it here. This tells it 1 or 0. If it is a 1, the network is fine. If it is a 0, we do back propagation and we update the network, the generator. So this generator second model that is learning from another model. You can imagine how complex and slow this learning is. It's because the dataset is not ready. We are just feeding something here, getting some image, and getting the results, which is the label, and the training this. It's like the labels don't exist in the beginning. Even the images don't exist. So it is training by another model, being trained by another model. And it can take a lot of time to train this kind of model, and they are very easily like they will like stall or stop learning very easily. So this is how GANs work. They are called generative adversarial networks.
So the generator could be autoencoder or any network on the.
Yeah, it's well, you can use an autoencoder for the coding, and then but you have like a second part that can generate the image or generate something. Because the autoencoder doesn't generate; it generates a second part. So you need a second part that creates the image or the song, or we have autoencoders, for example, for songs, or autoencoders for videos, as long as you have a good discriminator model that can tell if it is good or bad. Give a mark, and the autoencoder will update its weight to become better. So it's clear that it needs a lot of time to train. It can be insane. Are you happy with this explanation, guys, how autoencoder works? So they have two parts. The discriminator model, which is a regular model that produces a mark to give it to an image, and the generator that learns from the discriminator. Are you happy with this explanation? Amal, you wanted to say something?
No.
Are you happy with this explanation, how it works?
Yeah, go on.
Yes, fellow. Mm-hmm.
I want to know how the discriminator works. How he can detect that this image is real or fake.
It's a simple model. You train it from a data set, from real samples. It's like a classification, if you prefer. So you have a data set of real and fake, but it should be very big, and it is trained, and they are labeled. They are not generated here. They are labeled. So you have a lot of images, for example, and they are labeled 0, fake, 1, true, etc. And it is trained on them. That's all. It is
regarding the noise
here,
or the generator.
The generator is something else now. The generator, the noise is just some information that the generator will use to produce the model. It can be an image, it can be a vector, it's just some information, some code from encoded information. We forget about it. It's not, for now, to understand it, it's not super important, although it is in reality. So the generator will produce an image. The discriminator is able to tell it if it's good or bad. If it is bad, backpropagation will update the model. If it's good, it doesn't. And the generator will learn from the discriminator. So the power of the generator depends on how good the discriminator is, and plus other things.
Reda, in case of image, I don't know, maybe it probably would be in the discriminator, but we need to detect object before saying that this object is not good.
Not necessarily, because an image doesn't necessarily, to generate an image, we don't need to know what object it contains. A discriminator can tell
but to validate
if it's real or not. Yeah.
But how it could validate if how it could validate if he don't know where is each object?
It is able to, well, if we don't do the localization, the model can still recognize that there is a cut or not yet there. Yes or no? The pure classification case, the model could tell if there is a cut in the image, but it is not trying to localize. It is trying to give a mark. The model is going to be a little bit complex here because it's trying to give a mark, but inside the neurons are able to detect when you have a good data set. They're able to detect if this image is good or bad. If, for example, the cat doesn't have eyes, it's like a face like this without any eyes. This model is, if it is trained well, if it is well trained, will be able to tell that this is a bad image.
Okay, I think the architecture that you are presenting here handle just the case of an image with one object. I think
it depends on this sample. If you have multiple objects, this sample will tell. For example, if you have multiple objects, multiple places, and only one of them is fake, so your sample will say probably fake. So if it is well trained,
I want to say this architecture, it seems to me that it won't detect multiple objects in the same image.
No, it doesn't. It doesn't need to detect multiple objects. It just need to score. And to score, we don't need the net. We can have the information about what objects we have inside the network. It is possible in the layers, in the different layers inside. The information is stored there in an encoded way, and it could be enough to give a score. The model might not need to localize exactly where the eyes is, etc. But the information that the network extracted could be enough to give a score. For example, let's say you have here, we have here this activation layers. So here, the last layer. So this is for eyes, this is for ears, this is for mouth, let's say. So each layer is able to recognize something. So here, say we have an eye. So here we have a 1. Okay, here we have a 1 because we have an eye. Next, an ear should be here. And another eye should be here, and the nose should be here, and the ear should be here. So this layer, the ear should have an ear here. Yes or no? It says 1 in this position. Then we have the fully connected layer. The fully connected layer, we look at everything. So it finds an eye here, a nose here, and an eye here, and but there is no ear here in these layers, in these activation maps. So this fully connected layer will say fake. It will be able to learn the distribution of features.
Yeah.
A little bit complex, but it should be fine to understand. So the network will understand the distribution of features, how the features should be distributed. But it doesn't need to localize them exactly. This is a big object, etc. But the distribution of features is enough to be generally to put a score, to give a score.
Okay. So even multi-object, it's working. Okay.
Yes, yeah, distribution of features. So if you have two faces, the fully connected layer will look if we have and my next to and my nose here. And for the second phase, the same thing. Some distribution of features that make sense. Okay.
Okay.
Perfect. And well, this is for when we are explaining. When if we look at inside of the network, we must not be even able to explain what it means, because it's a complex function that represents reality, that can assess reality. For example, if a face is photographed just at its half, the person is turned around. These kind of things, they can also happen. But the network should be able to learn it if it has a good data set and a good enough architecture. Okay.
Yeah, Reda.
Uh-huh.
So does it mean that we are generating data or like new data because we are using noise?
Yes, we are generating new data. Yeah.
Yes.
Not exist.
And then we discriminate it with the discriminator in order to build
the second model, the generator.
Yeah.
This will tell yes, no, and this will learn. It's not just like a pupil here. Is drawing, learning how to draw, and this one is giving it feedback. You did well, you did bad, you did well, you did bad, but it needs to do a lot of attempts, many attempts before converging and becoming an expert.
And this is how the learning happens.
Exactly, yeah.
Nice.
It's like we are decomposing the learning to make it easier. I think the guys who developed it are now, I'm not sure if they are with Apple or with Tesla, somewhere like in one of these places. Okay. So some problems that can occur when the teacher is not good enough. Yes.
Can we use this technique to augment
the data set? It is possible, yeah. Although a bit dangerous. It can be a bit dangerous.
Dangerous.
Because the probabilistic distribution can differ from your original data set with this model, but you can still do it. The problem is that with images, doing rotations, zooming, etc., is an easier way to do data augmentation than these techniques.
Here it seems neurons are playing the role of genes.
I won't say genes, because genes are just doing things randomly. Neurons are just like functions, playing the role of functions, of simple functions that are combined together to make more complex.
I mean the biologic genes.
I'm not sure.
Genes of a human. Anyway, it's not.
It's probably no. It's not that. It's the noise that makes this gene. This code, this code that goes here, and the generator transforms it into the image.
It was just a joke, but I think that you didn't get it.
Possibly.
I was saying that the human genes they generate different different human.
They don't generate. It's the process that generates. The human gene they have the code. The information.
Yeah, they have.
That's why I told you this noise is the code, and the processes are what generates the human.
Yeah, so the genes are the neurons that are in the generator.
No, not really the neuron, because the genes are, like I said, are just the code. You have the processes inside the cell that duplicate the cell that makes all of these interactions to create more cells, etc. So you have the information and the process that's or the trigger of the process. But this is the more complex thing.
Okay.
It's like the process is also encoded inside the gene, etc. One of problems of GANs when the teacher is not well defined, or the model is not well built for the generator. We only capture the global structure. You can see what we developed. So it's like animals with multiple eyes. Like this is barely recognizable. So we can have these kind of problems depending on the teacher model, the discriminator. and how good it is. You can see that. Another problem when it is working well, for example, here, we are collapsing to a single model. We are not having like multiple variants. You can see it's almost one single model with slightly some variants, some variations to it. So yeah, so these are called early collapsing. It's that the model doesn't want to move from what we gave it, and it will always produce something close to the original thing. So I think we are done to the session. I know it was a very long one. Sorry, guys. Wow, it was a really long one.
It's fine. I'm sorry for the late beginning.
It was my fault as well. I haven't updated the calendar.
Okay.
So, guys, any question? I know it was overwhelming today, probably, but I just want you to know that this kind of things exist and how, more or less, how they work. You don't need to to be a master to do these things, but just to know a little bit how they work. I
think on TensorFlow there is GANs. We should find the GANs.
I don't think, I'm not sure, but there are open source libraries where you have GANs.
Okay.
Any question, guys, so far? So thank you also a lot for your attendance and your focus.
Thank you too. It was great.
Thank you, guys.
Thank you so much.
Thank you very much.
Appreciate your teaching.
So are you happy with today's session? Also, it's it was very dense, but you know that this technique exists and more or less how they work. Fine.
I think I'll have to go over your videos quite a few times.
Yeah, but probably you missed a few of them.
Sorry.
I said you missed few of them. A few sessions.
Yeah, not maybe a couple.
Okay. Yeah, you feel free to, of course, to have a look again. So I gave you guys 2 exercises. I'm going to add 2 more. One, to detect how many number of objects we have in a picture, for example, fruits or whatever. Like to get them. It's more now of a regression problem rather than a classification. So before that, I gave you the exercise for MNIST. Try to add to do the modifications, and then the data set about the type of hair, curly hair, straight hair, or I don't know what's the third class. This data set will be a competition between you guys. I want to see which one of you will get the best score. I will divide it into 2 testing and training, and we'll give it to you, and we'll see which one of you will get the best score, the best accuracy on testing. The third.
You said you said you give us 2. I don't remember the first one. The last one, which the one.
I will send an email about all of them. Don't worry.
Okay, it's good.
The third one is about regression. Detect how many fruits, for example, you have in a picture, or maybe the weight of a basket from just the picture. And the fourth one will probably be about localization or semantic segmentation.
Okay.
So yeah, I will give you, well, depending on your availability, you tell me when you are ready, so we can start the next part.
You can send it when you want.
Yeah, sure. So thank you, guys, and keep in touch.